The next method used in advanced microarchitecture in order to speed the execution of instruction is out of order processor design. So out of order processor means what? It is a type of processor in which it is used to overcome the data dependencies problem. How it is overcoming the data dependencies problem? This processor can execute or issue the instructions in a different order other than the actual order of the program that is written by the programmer, right? So this program or this processor can issue the instructions in a different order other than the actual order in which the instructions are written in the program, and as long as the dependencies are honored, right? So it will execute the instruction in a different order other than it is written in the program, and the dependencies will be met, so that the program will be generating the intended result. So out of order processor means, from the name itself you will get the idea, instructions will be issued in a different order when compared to the actual order in which the program has been written. So we will see one example for the out of order processor execution. So let us take the previous example itself. This is the actual program and this is the actual order of the instructions. But in the out of order processor, you can see the order of execution of the program has been changed. First of all, it has taken the LDR instruction. Then instead of taking add instruction, it has taken OR instruction as the second one. Then instead of taking sub instruction, it has taken the store instruction. After that, add and sub was taken. Finally, AND instruction was taken. So why there is a change in the order of the program? It is decided based on the dependencies. So here you can see LDR and AND instruction, it is dependent on R8. STR and OR instruction, it is dependent on R11. Sub and AND instruction, it is dependent on again R8. So based on this data dependency, the order of the program has been decided by the out of order processor, right? And this has been selected in order to avoid the pipeline stalling stages also. So when it is removing the data dependency, the stalling problem is also stalled. So we will see each cycle by cycle execution in the forthcoming slide. So here the processor can issue up to 2 instructions per cycle because it is a two-way out of order processor. So the processor can issue up to 2 instructions per cycle from anywhere in the program, depending upon the data dependencies. So from this program, any 2 instructions will be taken for each cycle as long as the data dependencies are met. So we will see the cycle 1 execution, what is happening in cycle 1 of the out of order processor. So in cycle 1, what is happening? The LDR instruction is issued as the first instruction. LDR R8, R0 hash 40. This instruction has been issued. And after that, add sub and AND instruction. Add sub and AND instructions are dependent on LDR by the way of R8. So add, sub and AND instruction, all the three are dependent on LDR through R8. So they cannot be issued in the first cycle. So only LDR instruction is issued. The next instruction add, sub and AND, since it is dependent on R8, they cannot be issued because R8 should be loaded with this instruction value, this address value. Then only it can execute the remaining instructions. So since that is not done, only LDR is issued. Then in addition to that, OR instruction is also issued. So in addition to LDR, since in the first cycle, each cycle 2 instruction can be taken, so OR instruction is also issued. So this is OR. Why OR is issued? Because it is independent of R8. So since it is an independent instruction, LDR and OR both are issued in cycle 1. Right? So in the first stage, LDR and OR has been fetched. In the second stage, decoding of LDR and OR has taken place. So for LDR, R0 and 40 has been decoded as from the or read from the register file and given to the ALU where addition is taking place. Similarly for OR operation, R5 and R6 has been read from the register file and given to the ALU where OR operation is performed, right? And after addition of R0 and 40, the result will be given to the data memory and the resultant address, the content of the resultant address. We have already seen, so the content of resultant address of data memory, content of the resultant address of data memory will be taken and stored onto or loaded to R8. But in OR instruction, data memory access is not required, so it is not shown in gray. The OR operation of R5 and R6 will take place. Resultant will be stored onto R11. Right? So in fifth cycle, R8 is loaded and R11 is written with the result of OR. So this is for cycle 1. Then in cycle 2, what is happening? There is a, you should keep in mind, there is a 2 cycle latency between issuing the LDR instruction and a dependent instruction. Right? So there is a 2 cycle latency between LDR instruction, because once the LDR is executed, after 2 cycle only you will be getting the results. Right? You will be after LDR, you will be getting the result only in the 5th cycle. So a dependent instruction can access this data only after 2 cycles. Latency of 2 cycles. So add cannot be issued because R8 is having the data dependency. Right. So in the next cycle, cycle 2, add cannot be executed or it cannot be issued by the processor because LDR will have 2 cycle latency. Only after 2 cycles are over, in the 3rd cycle only the result of LDR, that is in this case R8, can be taken by an instruction. So in the 2nd cycle, add cannot be executed as R8 is not available from LDR. Then sub writes to R8. In the instruction, sub is writing to R8. So it cannot be issued before the add. Since the add instruction was not executed here, sub also cannot be executed, because according to the program, what is written in the program? R8 should be read by the add, then only R8 should be written by sub. Add should read from R8, then only sub should write into R8. So since add was not executed in the 2nd cycle, sub also cannot be issued because sub can only write into R8 after reading the R8 by AND. So AND and sub cannot be issued. Then but only str instruction can only be issued here. Why str can be executed here or issued here? Because str is dependent on R11. R11 has already been written with the result in cycle 1. R11 got the result in cycle 1 as part of the OR operation. So in the cycle 2, only str can be executed. Right. So in str, what is happening? R11 and 80 is decoded and it is read from the register file. It is given to the ALU. In ALU, those two R11 and 80 is added. Right. And the content present in the resultant address. Right. To that resultant address, R7 will be written. Because it is a store instruction, content of R7 will be written or stored to the resultant address. So at this point we will be getting the resultant address. To the resultant address present in the data memory, content of R7 will be written. So store operation is over. And here you should keep in mind, in cycle 2 only one instruction is issued. The second instruction is not executed. So those logic remains unused. So this is in cycle 2. Only store is issued and sub is not at all issued. Then in cycle 3 what is happening? In cycle 3 R8 is available. This is cycle 3. This is a cycle 3, cycle 1, cycle 2, cycle 3. In cycle 3 you can see that R8 is available for the execution unit. Right? Since R8 is available, add can be issued. In cycle 3, R8 is available in the cycle 5. So if you are fetching an instruction here, in the second stage decoding will take place, third stage execution will take place. At the time of execution, R8 is available. So since R8 is available, both add and sub can be executed simultaneously. Why? Because add and sub are dependent on R8. So both can be executed. And again you should keep in mind, sub should write the result into R8 only after R8 has been read by the AND. Sub should write into R8 only after R8 is read by the add instruction. So that is taken care here. Sub issues simultaneously because it will not write to R8 until add consumes R8. Right. So here you can see that add instruction is taking R8 and 11, R8 and R1 in the cycle 4. Both will be added here. Right? How both are added? How it is getting R8? R8 is forwarded from load instruction. Right? Since the load instruction can generate R8 only after the data memory access, at this point R8 is available. So from this cycle, fifth cycle of LDR, R8 is taken by the AND or forwarded to AND. Then R1 is available here. So R8 and R1 is added. Resultant will be stored onto the R9 of register file. Right? So R8 is accessed. R1 is added with R8. The resultant has been stored. Right? So in the same stage only, sub is accessing R2 and R3. So sub is accessing R2 and R3. It is connected to ALU where subtraction operation is done. Right? Once the subtraction operation is done, it will write the result to R8. So the writing of the R8 was done only after reading of R8 by the add instruction. Right? Because the read operation of R8 is taking place in cycle 5, but the write operation by sub will be taking only in cycle 7. Right? So this issue is solved. Right? What is the issue? R8 should read, add should read R8, then only sub should be able to write into R8. Right? R8 will be read by the add instruction. After that only sub should write into R8. So this problem is solved here. How? Because add instruction is accessing R8 in cycle 5 for performing the addition, and after performing the subtraction, the result will be written to R8 only in cycle 7. So in cycle 5 R8 is read, in cycle 7 only R8 is written. So there is no problem. Right. So add and sub both can be accessed in or issued in cycle 3, so that they can be executed parallelly. So in cycle 3, since R8 is available, both add and sub has been issued. So next we will see the cycle 4 execution. So in cycle 4 remaining only AND instruction is there, and instruction will get executed. Why it is getting executed? Because R8 is available. R8 is available as a result of sub. right? So how this AND instruction is executed? R4 and R8 has been decoded for performing and R4 and R8 will be given to the ALU where AND operation is performed. So R8 will be given directly to ALU, R4 will be given directly to ALU. From where does R8 get? R8 will be available from the result of sub. Right. In the previous statement, after performing the sub, R8 is available. Right. So once the execution of the logical instruction is over, the result is available here. But in the case of load, once the execution of data access stage is over, then only the result will be available. But in logical and arithmetic operation, once the execution is over, the result is available. So in stage 6 or cycle 6, the resultant of sub, that is R8, is available, and that R8 will be forwarded from sub instruction to AND instruction. It will be forwarded from 6th stage of sub to AND instruction. So R4 and R8 is available and operation will be taking place. Since it is a logical operation, memory access is not there, so it will be returned to R10 as shown in the figure. Right. So the out of order processor issues 6 instructions in 4 cycles. So total 6 instructions has been issued in 4 cycles. First cycle, second cycle, third cycle, fourth cycle. So in 4 cycles, total 6 instructions has been issued. So what is the instruction per cycle count? 6 instruction by 4 cycles, 6 by 4, that is 1.5. So this is how out of order processor is executing the program or speeding up the execution of the program by rearranging the order of the program statements or instructions in order to handle the dependency. And here we have seen that there are different kinds of hazards occurring in the out of order processor execution. There is a chance for various hazards. So that is what we are going to see in the next slide. So first hazard is read after write hazard. So read after write hazard is occurring in 3 locations in this program. So first one, it is occurring between the dependence on and on LDR by the way of R8. It is occurring between the dependence on and on LDR by the way of R8. What does it mean? Both add and LDR is dependent upon R8. Right? So what do you mean by read after write hazard? What do you mean by read after write? The add instruction, the R8 present in add should only be read after the writing of the data memory, content of data memory to R8. So R8 in add should be read only after write of R8 in LDR is over. So once the LDR has been written to R8, then only add should read. If it is not happening, then read after write hazard will take place. Similarly, in the case of OR and store, the same thing will be happening. R11 of store should only be read after OR instruction has been written to R11. Right. R11 of str should only be read, R11 in str should only be read once the write process of OR to R11 should be over. Right. So R5 and R6 will be ORed, result should be written to R11, then only R11 in str should be read. Right. If the str is reading R11 before this write process is taking place, then read after write hazard will take place. Same thing will be happening here. R8 of AND should only be read by the AND instruction only after writing of R8 in the sub instruction is over. Once the R8 is written, then only AND should read R8. If it is not happening like that, again read after write will take place. Right. So this will limit the speed at which program can be executed, even if infinitely many execution units are available. Because of this read after write hazard, it cannot change the order, so it will limit the speed of execution. Why? Because let us take in this case, only after completion of sub, then only add can access write. Only after the write process of sub is completed, then only AND can read this write. So what will happen? This will limit the speed because parallelly this instruction cannot be executed. So it will limit the speed of execution at which the program can be executed, even though infinitely many execution units are there. Right, here we are having two parallel execution units. Even though we are having that, this cannot be accessed parallelly, so it will limit the speed. Right, so this is known as read after write hazard. In this program, three places it is occurring. Second one is known as write after read hazard. What do you mean by write after read? This is one example. Right, so sub is dependent upon add by the way of write. So what do you mean by write after read? Sub should write into write only after sub should write into write only after the read from write in add is over. Right, sub should only write into the write once the read from write has been completed in AND. Right, because in AND operation, first operand is present in R8, second one is present in R1. So both these operands should be read, addition should be performed, then it will be returned to R9. So once this read, the R8 is read by the AND, then only by the add instruction, then only write process of sub can take place. If the writing of R8 in sub is done first before the add has read from R8, then write after read hazard will take place. So add should be executed first, then only sub should be executed. Right, and write after read hazard cannot occur in a simple pipeline architecture, but it can happen in out of order processor. Right, write after read hazard will not occur in simple pipeline. Why? Because in simple pipeline the order of execution is maintained. We are not going to change the order. Only after add is executed or only after add is issued, then only sub will be issued. There is no change. But in the case of out of order processor, this order can change. So if sub is given the CPU time or sub is executed before add, write after read hazard will take place. Right. So that is about write after read hazard. So write after read hazard, why it is happening? Write after read, it will be happening because of the use of same registers for two unrelated instructions. Actually add and sub both are unrelated instructions. Why this write after read occurred? Because the same register R8 has been used in both add and sub. Since R8 has been used in both add and write after read hazard has taken place. So if the sub instruction, instead of using R8, if it has used some R12 or R10 it is used here. So let us take R12. So if sub is using R12 instead of R8, this write after read will not occur, because add and sub will be totally independent. Why? Because sub will be using R12. So if R12 was used in case of R8, write after read will not occur. But why the programmer has not used R12 here? Because this may be one of the reason, because ARM architecture is having only 16 registers and the programmer sometimes is forced to use or reuse the same registers because all the other registers may have been used in the program somewhere. So at some point of time, the programmer is forced to use or reuse. The programmer is forced to reuse the same register instead of using another register, because all the 16 registers has been, or all the remaining registers has already been used in the program. So because of this problem, generally write after read hazard is occurring. Then the third hazard is known as write after write hazard. Right. So write after write hazard is an output dependence problem. Right. So write after write hazard occurs if the first instruction attempts to write into a register after the second instruction has already written to it. So let us take these are the two instructions. So here if the first instruction is trying to write into R8 after executing the add instruction. So let us take LDR is first instruction, add is second instruction. So in the normal case, LDR should write into R8, then only add should write into R8. But instead of that, in the out of order processor, if add instruction is executed first, so what will happen? Add instruction will add R1 and R2, resultant will be written to R8. So add instruction has written to R8, and after that if LDR is trying to write into R8, then write after write hazard will take place. So how it is taking place? Add instruction should only write into R8 once the write process of LDR is over. Add should write into R8 only after LDR has written into R8. That means LDR should write into R8 first, then only add should write into R8. If it is not done in that manner, that means if add has written first before the LDR write process is completed, write after write hazard will take place. So this hazard will result in a wrong value being written into the register. So here according to the program, add should write only second. So instead of that, if LDR is writing last or second, then the value that is being written to R8 will be wrong. The final value of R8 should only come from the add according to the program or order of the program. If you are trying to reverse it, or if the out of order processor is trying to reverse the order of execution, then write after write hazard will take place. So these are the three different types of hazards that has to be managed in out of order processor execution. Next we will see what do you mean by scoreboard present in an out of order processor. So out of order processor uses a table to keep track of all the instructions waiting to be issued. It have a table which is keeping track of all the instructions that are waiting to be issued. This table is known as a scoreboard. It contains all the information about the dependencies. So this is a table holding all the instructions which are waiting to be issued and its corresponding dependencies. So the size of this table, that is scoreboard, determines how many instructions can be considered for issue. The size of the table determines how many instructions can be considered for the issue at the time. On each cycle, the processor examines the table and issues as many instructions as it is designed for, which is limited by the dependencies and the number of execution units which are available in parallel. Right? So in each cycle, the processor will be examining the table or going through the table, and it will issue as many instructions that is it is designed for, and which is limited by the dependencies and by the number of execution units such as ALU, memory, etc. which are available. Then the instruction level parallelism is a number of instructions that can be executed simultaneously for a particular program and for a microarchitecture. So that is meant by instruction level parallelism or ILP. So ILP is nothing but number of instructions that can be executed simultaneously for a particular program and a microarchitecture. So this is what is about the out of order processor design in the case of advanced microarchitecture.